is a test charge. And if we place this test charge in the region that has the electric field, and how can we know that there are electric field? We can measure this by measure the force on this test charge. So it means that if you place a test charge somewhere and if you feel the electric force, if you can feel the electric force on the test charge, it means that we have the electric field. Okay? Anyway, we know that the force is depend on the amount of the charge, of the test charge. For example, if we know that this electric field comes from another point charge, okay, if we have another point charge here, like this, and if this has a charge Q, okay, we know from the Coulomb law that F is equal to the K Q0 Q over R squared. Okay? Where R is the distance between these two charges. Okay? So, you can see that the magnitude of the force depends on Q0 or on the test charge. If you use the test charge that have a large amount of charge, the force will be large, right? If you use the charge, the small Q0, the force will be small also. The problem is that this electric field comes from the same big Q. So, we should assume that the electric field from this charge should be the same. It's independent of the test charge, right? Because it is a electric field from the same. In this case, if I fix the big Q here, so it means that this electric field should be the same. It should not depend on the value of Q0, right? Because this is the electric field from the big Q. But the force depends on Q0 from the Coulomb law. So it means that to eliminate the effect of Q0, we should divide this F by Q0, right? You can see that if Q0 is linear, it depends linearly on the Q0. F is from this relation, F is linearly dependent on Q0. So it means that if we divide F by Q0, you will eliminate the effect of Q0, right? So the way we define the electric field is that once we know the force on the test charge, we divide it by the charge of the test charge. And this ratio F over Q0 is defined as the electric field. Okay? The ratio of F over Q0 is defined as the electric field. And this is a definition of the electric field. And here I show the example of the point charge. But this definition can be used in every cases. Meaning that this is a general definition of the electric field. That is, the force on the test charge divided by the amount of the charge is the electric field. Okay? and unit of the electric field is the unit of the force divided by the unit of the charge, right? So unit of the electric field is the Newton per Coulomb. And later you will see that we can write down the unit of the electric field also as the volt per meter. And in many cases, this unit of electric field is useful. It's much more useful because you will see that it is more useful to explain the electric phenomena in terms of the potential difference, the volt here. So the second unit is quite useful, the volt per meter. Okay, and that is the definition of the electric field. Next, this definition is we may say that it is like a simplified definition, a simple definition. In general, somehow, if you look at some textbook, in some textbook, they may use this definition. But in some textbook, they will write it in more mathematical way that the electric field is equal to the limit of Q0 approach 0 of the ratio of F over Q0. Why we have to put the limit Q0 approach 0 here? The point is that in this definition, I show the example of the I assume you can see that I use the Coulomb law here, and we discussed yesterday that we can use the Coulomb law only when the charge is a point charge, right? So it means that the charge here and the charge here is a point charge, okay? And we can use this relation, but in general, we don't have the real point charge. If we have an object, for example, if we have the test charge Q0 here, and it is a material that we have the charge on this object, and if I want to measure the charge, the electric field from this object, we have the big Q. The charge is big Q. The problem is that when we say that we have the charge on the second object, on this object, it means that we have a small charge distribute on this object. And once we put the test charge here, for example, if the charge on this object, is positive, for example, it's a positive charge distribute on this object. And if I place the negative charge here, if it's a negative charge, what is the force between Q0 and big Q? It is an attractive force, right? So it means that it will attract the positive charge on the big Q. The situation will be that the positive charge that distribute on the big Q will try to move as close as possible to the test charge. So it means that first we may have the charge on the big Q distribute uniformly on the object. But when we place the test charge, this test charge near this big Q, the positive charge on this big Q will try to move to this side. So it means that the distribution of the charge here is changed. And it means that the electric field that we measure from the test chart here is not the electric field before we have the test charge, right? If we don't have the test charge, the positive charge will distribute uniformly on the object. But when we place the test charge here, the positive charge try to move to this side. So the distribution of the charge on this big Q change after we place the test charge. So it means that the distribution of the charge on this object change after we place the test charge here. And that is not what we want. If we want to measure the electric field of the charge on this big Q, it means that the test charge should not disturb the electric field itself, or it should not disturb the distribution of the charge on this object. So that's why we have to take the limit Q approach 0 here. The meaning of Q approach 0 here is mean that the amount of test charge should be as small as possible. And when the amount of test charge is small,